can, I don't know, just mute and ask or write on the chat, and then we can read at the end. But I'm a little bit afraid since we have another astrophysicist in the crowd, so maybe Valentina will call bullshit of anything that I say. So let's see. So yes, so this talk is kind of, I hope that everyone can read the slides and you can see. I mean, I know that there is the background, but yeah, long story short, I'm sharing the whole desktop, but I hope that you can read. So this talk is kind of a mix between previous talks that I had, and I tried to put them together. It's kind of like story experience Python physics talk. And I tried to remove most of the scary parts. I just left one there, just for you to get more close to the topic in general. So so this talk is mainly about the experience that I have doing astrophysics during my PhD. It was mainly playing around with stars, black holes, and of course, Python. If you have any question, of course, you can find me there later, or you can write on the chat. So I studied computer science, and I started studying in 2006. And the situation back there, at least for me, was that I was really into scripting. I was doing many things with Perl, Bash, and Python was still something that, at least in my universe, it was not really widely used. One of the nice things I remember reading when NumPy 1.0 was out, and it was like, ah, cool. So something about arrays and stuff, but I didn't even care much. So while the years were advancing in 2009, Python 3 was already out, but of course 3.0. And still, at least in my university, there were like, Perl people all over the place writing complicated lines, and other people that we started to look into parallel computing, but of course we're having a C background. And back then, I remember that I went to a conference that there was the authors of MPI for Pi and PyCUDA were giving some talks, and I was like, so apparently you can use this Python thingy in a more professional way. Maybe at the end of this year or in the middle of this year, there was also this kind of, I don't want to call it fight, but dispute between Django and Ruby on Rails, because of, everyone wanted to do these scripting things in web applications. And so Python was, at least in my world, was starting to become more popular. So when I started my studies at the PhD, more or less, I mean, high Python was still not a thing around the people that I had in the uni. Notebooks, no. I remember that I was using IPython because it was kind of nice to have all the history of the commands that you were using, but in any case. Pandas was like, what? No, but I think that it was 0 point something, or I don't remember the version of Pandas. And a friend of mine that was doing some forecast simulations who told me like, oh, there's a new thing called scikit-learn, and it was like, yeah, well, whatever. I mean, Pandas, scikit-learn, yet another Python module that will not become popular, right? So in this situation, it was like kind of really against, I don't want to say completely against, but like Python was maybe some toy to play around with. But in any case, it's something that I really like. I mean, it was really simple, and other people were really keen into understanding what was going on. So, okay, I had some experience. I was teaching some Python basic, but it was okay, so maybe I can use this. So when I started I decided to start astrophysics. And just a disclaimer, when people talk about astronomy is a natural science in general. Sometimes people also refer to astronomy with observational astronomy, so people going to telescopes or maybe manipulating some radio telescope, which is just antennas. And when we are talking about astrophysics, is something that is inside astronomy. And we are kind of like, we're studying the nature of all these celestial objects there. And even though it's called astrophysics, it's used a lot of chemistry too. So that's kind of like the main difference of astronomy and astrophysics. If you have a question that is on the screen at the moment, I think that I will literally jump out of the window. Astrology has nothing to do with this field. It's a pseudoscience. So let's go. Why astrophysics? To be honest, I mean, when I was finishing, I was really into high performance computing, and I got really tied into programming GPUs. Back then, I was using CUDA. Maybe most of you have heard, and now you can like write one line, and suddenly you have your machine learning models on the GPU. And but there was really cool because C extensions, you were handling memory by hand, and I don't know, I was really into C, so it was a really cool thing to do. But most importantly, there was this talk. Since I have the desktop, maybe I will just show it. So there was NVIDIA was showing some stuff there at some point, and they showed these simulations. I hope that you are following it. It looks really cool, right? I mean, I know when I saw this thing on a conference, an NVIDIA conference, I was like, oh my God, how you can do that? I want to do that. So this thing was called embody problem. And then I started to read about it. So after reading and everything, okay, I packed all my things. I arrived here in Germany, and I was what I was expecting from a research institute, widely known with research stuff. From my computer science background, it was like, okay, so they will have some version control systems, software with documentation, tests, implementation details. I was kind of like willing to use all the tools and secret weapons that I had for my studies, right? I mean, robust frameworks, using the latest programming languages that help me in astrophysics doing stuff, and of course, mainly science. So what I found when I arrived there, and of course, this is really specific to my center, but after talking with many people, it was kind of like the same scenario back in 2012. So people were sharing code with the zip files or target sets, and until today, one of the most important people with this embody problem that I show you is that they have their own website. It doesn't matter if you cannot read, and they have all the versions there. So this is version control as a la astrophysicist. And okay, so fair enough. Yeah, well, can download, compile some stuff. There was no documentation whatsoever. I mean, some comments were like, I remember still some comments like, we are using 3/4 here because it empirically it works, but we don't have a reason for it and stuff like that. All of our simulation code I was using scientific papers, of course. Implementation details or documentation on how to use it, this nice like quick start stuff, it was completely missing, but there were many scientific papers that were highlighting the mathematical models behind, so you can get a general idea. There was no frameworks, to be honest. And this programming language dominating astrophysics, at least in my center, was Fortran. There were some people brave enough to do stuff in Bash to automate stuff. And I met a couple of people, they were playing around with Python, but they were just not using it. If you're not familiar with Fortran, first of all, you are really lucky. But if not, I just want to share. So for example, here you have some Fortran code. If you are not familiar with it, it's really painful, at least for me, to read it. And it's a language that, even though it's fast and whatever, it's really not kind of like approachable. But there was science, so that was cool. So, okay, so I was mentioning before the embody problem, and I wanted to work on this start thing. So there will be some math now ahead, but don't worry about it. I will try to explain everything there. So the embody problem is that mainly solving this equation there that you see, which maybe could seem for you a little bit hard, but just believe me, it's not. You will see a prototype afterwards. It's 300 years old, and this comes from Newton. This is Newtonian physics. So this is nothing else than the interaction of two bodies there. You have r, which is just distance or the vector of distance, and you have here acceleration. 2 dots is because it's derived twice. So you derive position, then you have velocity, and then acceleration. And usually this is the description of, or the physics behind, things that are called stellar systems, or maybe you heard about globular clusters, or maybe you saw some nice pictures at the one on the right, like many stars together. So this is a globular cluster. Okay, so I started to read a little bit about, and then there were like many different approaches to solve this simple equation. There were like things called tree code. There was like kind of like divide and conquer in a hierarchical way. There was really crazy extrapolation methods like the FMM, the fast multiple method. And there was a more naive approach that is just applying the same formula that you saw. It's called direct summation. So I thought, okay, if I want to start, let's go for the O(n) square. So first of all, reading all these scientific papers and stuff was kind of complicated. So I needed something by hand that kind of like was easy to write, easy to understand, easy to debug, and try to play around with it. So I started to use Python for everything that I was prototyping. And as you can see, the formula on the right, on the left, it's nothing else than the formula on the right. I mean, of course, inside formula calculation, you have some subtractions and maybe some multiplication. You have some structures storing everything, but this mainly I mean, it's nothing else besides this. So, okay, simple enough. So I decided, okay, I will just stick with Python and try to use it with many other approaches. So I started to use it mainly for automation stuff. Usually the systems, the one all these stars together, there are like many theoretical things that you will write about, like how to generate the initial conditions. And I was using one of these, it's called Plummer sphere, but again, just a formula that you get random points, and then you have this kind of the same structure. So in the meantime, I just want to highlight that, I mean, when you say astrophysics, usually maybe what comes to your mind is like, I don't know, people doing real science, like for example, this photo, or like people doing real things like in labs and stuff. That's experimental astrophysics. So what is theoretical astrophysics is more or less what we are all doing now, sitting behind a desk on a computer, running some, some simulations and stuff. So far it's really simple approach. So in theory, everyone here can kind of start playing around with these things. But of course, all the simulations are quite demanding, and you need to have like access to giant clusters with hundreds of nodes and stuff. So another thing that I did, it was kind of generating, initial conditions, and also all this. This is kind of an example of a submission script. So it's just a bash script, how to submit this to the local cluster I used to have. So many things start to repeat here. Like for example, okay, I want 16 nodes. I have here 16 too. So all these things were automated, and I had some magical script that was generating this for a range of cores or number of particles for this set of stars. Something else, of course, was data processing. Since I was really beginning with Python, I was relying mostly on the OS model, listdir and everything. I mean, patlib was still not a thing. When I was unpacking binary structures, I was using the struct model that I don't know if many of you know it, if you want to handle binary data. And the fancier thing that I learned, it was like if you were using NumPy load text, was kind of slower compared to the gen from text. So I was the Python expert because knowing that. But then you guys, yeah, but if you're working with data and stuff, what about pandas? Back there, it was like, I think at 2012. So it's not still a thing. And even though many people started to use it, I was not really into trying new stuff because of course I needed to finish experiments and everything. So of course, other really important aspect is after you process all those data, you can have nice combinations for a scientific paper, like using matplotlib and LaTeX. And you can have, just random plots there for like following LaTeX style. So in this case, for example, this is how the system evolved and scale with different amount of particles using OpenMP. This uses, I think it is MPI, and this is using multiple GPUs in different systems. So you see they're scaling. This is the number of particles. So stuff like this was kind of like an everyday thing. So Python started to become my go-to tool to automate stuff. I was even at some point automating email sending because there were some conference that we were organizing. There were sometimes that I needed to send information inside the institute. So I was even relying on Python to write small scripts to send emails, for example. I don't know if you know that you can configure maybe your emap or POP3 server and then just write mail -s whatever and just write an email from the command line. But stuff like that was easily to automate. But so far it's like, yeah, okay, it's like automating a couple of things and your life was easy and stuff, but it's kind of boring so far. So this was one of the most entertaining things that I started to use. I didn't know anything about OpenGL, and I started to write a data visualization tool from all these n-body simulations. As you can see there, It was one of the first prototypes. The tool then later on I rewrote it in C++, but originally I was writing this with PyOpenGL, and it was really straightforward to kind of ended up having this visualization, which also looks really nice. I mean, if I show you all the plots, but if I show you this, it was like, oh, cool, some stars and points. And there was also some really things that I started to use Matplotlib a lot, and I started to do many custom plots. So in this case, it's a simple plot. I started to make some color for some specific of the stars. This is again the same thing more or less that we are looking at here. And there is a phenomena that I wanted to study at some point. It's like the red dots. Maybe you don't see the red, but the dark colored stars here, they tend to go to the middle of the system in a phenomena that is called core collapse. So I did this with Matplotlib, and then I had some animation at some point, but I couldn't find them. And then I had, like, you know, after a couple of time step, I can easily see all the darker things there. So I was really hugging into Matplotlib. There are many things that were not possible to do so, and I guess that was the idea that many other frameworks started to born from Matplotlib. But yeah, I mean, the Matplotlib script that I had was but it was really cool because nobody else was able to do this. They're using nuplot and stuff, but it was really complicated and not portable. And I don't know, I started to feel like Python was really like my like main weapon for solving any problem that I had during the studies. So that was a part of the stars. So regarding all the black hole part of the story, black holes are still a mystery, and maybe you remember from media some news about it, but still we know nothing. And the thing about theoretical astrophysics is that we write papers, we have stuff, and maybe in couple, maybe in tens, maybe in hundreds of years, someone will say, no, you were wrong. This was the original. But so far, we have no idea what is inside a black hole. That's why we still call it a black hole, but maybe there is some interesting particle inside. So I just usually I interact a lot with people since we don't we cannot interact much. I just wanted to see if some of you knew this photo. I will expect maybe some hands on the audience, but in any case, this is LIGO. So this is an experimental facility that has these really long arms, and they were sending laser beams to each arm at the same time. So imagine something like coming from here and then from there. And then there were some mirrors at the extreme, and the thing was coming back. And what they were measuring was that when the laser came back, did they were at the same time? And we are talking about here of like precision of 10 to the minus 20 something meters. So it's really, really something really crazy small. Maybe this is not familiar with you, but maybe the word gravitational wave, it's more familiar to you. A couple of years ago, there was a Nobel Prize on physics was a gravitational waves. So what they detect was a simple gravitational wave that was coming from the collision between two black holes. So when two massive objects in the universe, like black holes or neutron stars, maybe you heard about neutron stars, collide, they are so massive that they free so much energy that they disrupt space-time. So this means like you can imagine this simply like imagine a lake and you throw a stone and then you see all these ripples going around. This is the same, but with space-time. So what does this mean? If I am receiving a gravitational wave, then my head will start to elongate and then to the sides, like an effect like a spring effect. But of course, this effect, this elongation, is something, as you can see, maybe here numbers 10 to the minus 20 something meters. So it's something really, really, really small. So you need really precise tool. So LIGO, of course, is located here on Earth, but there are many other projects that are coming in the future. And one of these I just wanted to highlight is this one here down here that I want to show you a video about it. It's called LISA, so the laser interferometer space. So I know you have no sound, but just imagine really like Inception music going on, like, you know. But the idea of this is grabbing the same, let me just pause here briefly, is grabbing the same idea that we have here on Earth but on space. So they will want to go crazy and launch the space rocket. And once the space rocket is up, they will start to, release all these different satellites. And in all these satellites, if you see there, they are like 1, 2, 3. There have been some modification of these projects, but they will be around the space. They will start to communicate between them. And they will start to see, okay, so where do we need to connect? And then shooting lasers. I know this sounds like Star Wars stuff, but it's not, believe me. And then they have these self-regulated things, millions of kilometers between the lasers. They will start to receive everything. And I said, okay, sure. We acquire the signal, and then we will have the fixed configuration that we will need to maintain. And these 3 satellites will start to nothing else that go around Earth and start to observe everything that we have around. So the same thing that we managed, you can see there is the following Earth orbit. I just want to return a posit, and we will see like many more like little spaces and corners in the universe that the project that I was briefly describing before can. So this is a mission that is already accepted. Is for 2034. Yes, space missions takes time, but this is something that will be really amazing. And maybe you will remember this talk, and in a couple of years you will say, "Oh my God, this was the thing that was in PyData." But I really believe that when that mission is out, physics will change completely. So also another really interesting thing about black holes is that you saw this Event Horizon Telescope pictures that you can see there. It's the picture of the black hole. But what we see there, all the brightness is just photons that are trapped into the Event Horizon, of course, of the black hole. And if you're interested in this, there was a Euro SciPy talk last year, really interesting talk by Sarah Eason. So maybe you can go there and see it. It's called In the Shadow of the Black Hole. Really interesting stuff. I really invite you to go there. But yeah, so let's go back a little bit back to reality. So what I was doing with black holes was like, we know Newtonian physics. So the physics that you learn maybe in high school or university, if you did something similar, things moving around, orbits. And as you can see in this animated GIF, you have Earth that is kind of a little bit faster when you go to the sun, then slower. This is what it's called Newtonian physics. Everything was calculated here on Earth. But as soon as we started to see things outside Earth, we started to really understand that maybe we were wrong. So have you heard about Mercury? Of course, a planet. I don't know if any one of you know any particular thing about Mercury, but I mean, of course, this is the first planet of the solar system close to the sun. But did you know that the orbit of Mercury is precessing? So you start here, and then it's kind of like tilting little by little, and then we have this kind of like rose shape. So nobody knew why this was happening until, of course, there was some more research and people start to understand that this was a new physics. So this was post-Newtonian physics. And for this thing, you have a set of formulas that you can apply. And in the case of if you have like 2 stars whirling around, or black holes or whatever, just 2 things whirling around, you can get some effects like this one, for example. You see the 2 different lines are 2 different objects. In this case, the lines resemble a black hole that is really close to merge with another one, because it will go whirling around and it will go together and together and together. And at some point, whoop, they will merge and they will generate this gravitational wave that I was mentioning. So you can model these things. There are some formulas that you can get approximations to this. But how do we really calculate these things? And for this, I just want you all to take a deep breath, because we will see some weird things on the screen now. Okay, so we start from this point. This is Newtonian physics. This is the same equation that I showed you before, but written a different way. The precession that we know from Mercury, it comes from the first post-Newtonian terms. There is another term, the second, that is called the energy. And there's the third that is related to all the spins of stars. So how do we calculate first post-Newtonian term? This is the equation. We have speed of light there, many different fractions, everything. Okay. This is the second. The second was so complicated and difficult to understand that you need a correction. So they invented the 2.5, which is a correction to the other one. And then you go to spin, you have a formula like this. And I'm sorry, but that's not complete. So you need the second part of the formula. So it's really, and then you have the correction of that spin. So, and then again, there was not the whole formula. So these formulas were a real thing, and I needed to work with them. For me, at least, it's impossible to start debugging something inside a huge framework. So I needed something easy to do it. So that's why I decided to go with Python. And all these systems relied on the energy conservation. So this is just acceleration of particles. But if you want to go to energy, you need to be consistent and also consider these things into the energy. Luckily for that, the equations were not really big, but still, there is a lot of things going on there. I don't expect you to even kind of like try to read these things. So this is real. I mean, I use this in simulation. The animation that you saw before, this kind of rose like, I implemented it. And you can see here, this is the final implementation in C++. You have post-Newtonian terms 1, 2, 3. And since I was working with the integration system that was working with the derivative of the acceleration, I ended up having these things. Again, I don't expect you, and I don't wish you to ever debug these things. Doing this thing in C++ at least was really complicated for me. So I needed to use Python. And without Python, I think that I would be unable to even understand if this thing was working or not. So it was really a live server, because even complex formula like this, you can write it in a simple way and trying to understand. So yeah, that's enough for maybe a couple of simulations, but it's this a real scenario. I mean, when we see the skies or the news, we see really nice pictures out there. And all these nice pictures that showed colors and stuff comes from complex solutions. So in this case, I was also using an existing piece of software written in C called Gadget. And this was a smooth particle hydrodynamics code. Sounds really complicated, but in a nutshell is, let's have your moving points and put some gas on it and some fluid dynamics inside the systems. So I was referring to these pictures, and you can see here, this is a really nice simulation of two galaxies colliding. The simulation of this animation is based on smooth particle aerodynamics. So in that case, all the things that you see around these bright spots is gas, because gas feeds stars, and then stars can go grow and grow, and even black holes can even get larger by eating stars. But how do black holes eat stars? This is something that also was really mind-blowing for me. We don't know. We assume we have different approaches to understand this. There are different things called, for example, Rochet-Lowe, that is kind of like some celestial mechanics calculations that you can kind of this 8 or infinite symbol that it depends on how massive the objects are. There are some people that really don't care much about this. Okay, I will define a radius on this black hole, and everything that enters will be swallowed by the black hole. And there are other approaches that say, hey, everything that is bound to the black hole, so this means that the energy is interactive strongly with it, it will be accreted. Accreted is a word for eating. Of course, we don't use eating in papers. So there was a lot of, again, different scenarios and configuration, how to play around with the gas. But still, I was generating static plots about it. So these are some pictures of many simulations that I ran. This simulation took months. There, all these orange, yellow, I don't know how good is your screen, are just gas particles. And these are millions of gas particles whirling around. So since I was using this software, I was doing this, I really needed to have something more visual. And then with Python, I was able to make something more nice, which is of course an animation. So here you can see two black holes rotating in the middle. I will just see. And then I started to do this really cool experiment that was throwing gas clouds to the binary. All the bright spots that you are seeing on the screen are areas where new stars can be born. So in simulations like this, you can see if I have two black holes, I will start generating stars. You can see also, let me pause this. You can see also some, maybe here, you can see some oh my God, sorry, this went. You can see some structures around the black hole too. So for example, there you can see some dense areas around it. So there are so many applications here that when we ended up having these simulations that that we didn't know where to start, and we ended up like having 2 papers and like ideas for all the like 4 papers. But we noticed all these things because of these animations made with Python. Of course, some people were looking at the plots, but usually plots were not about the whole evolution and all simulation. We were looking specifically at these animations made with Python, and it was really helpful to understand. So this is another simulation that I just want to just show you that things are kind of different. In this case, the clouds are being thrown in a clockwise, while the black holes are counterclockwise. So you see some kind of ring there that is being formed. This is really cool, and it's a really nice ring that I was really happy about it, but it gets destroyed now when this new cloud, see, no ring anymore. So there was many conclusions that, of course, I don't want to go into details, but structures were not really stable in this. But again, there are many things there, and I think that I still have multiple clouds. If you're really interested to see more movies about these things, if you go to multipleclouds.xyz, I have all the videos there of the simulations. So if you're interested, you can go there. So when I started working with these things, most of these things were little scripts. People that were writing Python scripts that do something, reading the snapshots of some program, generating this nice animation, and so on and so forth. Another use of Python back then was people wrapping around C libraries, as we saw before, MPI stuff, CUDA. And there were people that wanted to go forward, and there was a really nice project back then, and I just recently checked it, and it's really, really well evolved at the moment. It's called Muse, so you can just there go and Muse code.github.io. So this is kind of a glue of many astrophysical pieces of code in one place, so you can interact with different simulations and start doing many stuff. And even to my surprise, last year at PyCon, I was listening to many people doing different things with CUDA and GPU computing that I thought it was only PyCUDA, but no, there was CuPy, JAX, Rapids. There are so many new things at the moment that I think that the scenario is really prominent and helpful at the moment. But this was before, right? So what do we have now? I think that what NumFOCUS is doing in general is, for me, is the second boost of Python. What do we need in general? I mean, scientists all over the world now, I think that they can easily start setting up Jupyter notebooks and maybe, using Pandas, NumPy, whatever. If you are more into simulations with Monte Carlo and Markov chain things, or maybe analytical mathematics, that things that you can do with proprietary software like MATLAB and stuff, you can still do it with Python, of course. There's also AstroPy. There is a project that when I heard about last year, I looked at it and it was delightful to read. There's a lot of tutorials and documentations, and I will have loved to have that thing before I started studying. So I really believe that if we know that the first rise of Python was, well, the second, maybe the first one, of course, the release, but Django kind of like positioned Python out there, then NumFOCUS and science in general is kind of positioning Python again as a de facto solution. I'm really curious to see in the next year, like what is the next step. So some people is saying that maybe mobile is the future of Python, maybe WebAssembly, maybe, I don't know, writing Python and running everywhere and just Raspberry Pi, microcontrollers or whatever, but really curious about it. So yeah, I mean, that's it. I really hope that this was not too boring or too deep or maybe too brief for your taste, but I would be more than happy to answer some questions now. If you have some other questions that you don't want to ask now, you can reach me there on Twitter or whatever. At the moment, I'm not doing science, but that's, I think, it's topic for another talk. But yeah, I think that I will be gladly to see like if there are some questions or something. Thanks.
Let's say a bit nostalgic. I wouldn't say boring.
Okay, so new question, I guess. No questions, I guess. So
People seem pretty happy. It's astrophysics. Physics. It's hard to give a talk that people don't like.
Yeah. Well, I tried to minimize all the formulas and stuff, but in any case, my information was there, so any person with some question can write me. Thank you.
I would. You mentioned a lot like using Python. I probably would have enjoyed a little bit more detail on that.
Yeah, well, the problem is that when I had the detail, but I started to remove slides because it was mostly Python code.
Oh, fair.
And I was not sure if there was, but yeah, maybe.
So was it that you ended up using just pretty much, like, as you said, NumPy and just the basic Python stuff and everything else from scratch? Lost your voice. Oh, well, why were you muted? Sorry.
I mute myself just to hear you, and then I couldn't unmute me.
Oh.
So yeah, everything that I was using there was NumPy. At the end of my studies, I started to work with Python, with pandas, and I was like, oh, fuck. So why didn't try this before? But yeah, mainly all the computational stuff was NumPy, PyCUDA, and I did some PyMC. It was not PyMC3, but it was another Monte Carlo Markov chain module to do some Monte Carlo stuff.
Yeah. Awesome.
Cool.
I guess we don't have questions. I'm going to allow people to unmute now. Oh, and stop recording.